Okay, so in the previous lecture we saw first 3 steps about constructing a root locus. First step was a little easy to understand, that it is actually symmetric about the real axis. Then we also characterized where does the root locus start when k equal to 0, and what happens as k goes to infinity. And then we concluded that they start at the poles and end up at zeros. And then what if there are more number of poles than zeros? The remaining poles go to as what we defined as zeros at infinity. We also easily computed to see if what areas of the real line are on the root locus. So that was just a small test based on how many poles and zeros lie to the right of that particular region of the real line. Okay, so continuing on that, so the next step here is how do the root locus branches go to infinity. For example, in the motivating example we saw that we had this guy pole here 0 and minus a, that they meet here and they go to infinity. Okay. Okay, now what decides this? Why don't they go something like this, right? Or why don't they go something like this? Or why don't they just, instead of going on a straight line, just follow a lazy path and do a little more adventure and go this way, right? So who decides how they go? Or maybe in this example it was a little easier because it was just like a solution of a second order or a quadratic equation, right? So what if there are more poles who meet at this point, and then there are, can they go to infinity in the way they want, or there is something that decides that, right? Okay, so the statement says that the n minus m roots, so we are only interested now on the roots or on the poles which go to infinity as k goes to infinity. So the n minus roots that proceed to infinity, they do so along asymptotes with this angle, right, and this is, which I will show you shortly how this is computed, right. So consider a test point at infinity, right. So okay, let us do a little this thing, just erase this and okay, and I say okay, let us say I have my sigma and j omega axis here, okay, and say this is my infinity here. Okay, so there is this guy S naught at infinity. Okay. So and then there would be open loop poles, zeros and whatever. Just say there are these two poles, right? And I say I just look at how the angle approaches. So it goes here and then keeps going here and then it reaches this guy. So this guy is still very far. So I just do something similar, right? I'll go here and then it will meet this guy here. Okay. So this test point which is at infinity, so what are these angles, right? So the angles made by the line joining the test point and the open loop poles are zeros, they are almost equal to each other, right? Because if I really look at 2 points from very far away, they will seem just very close to each other. Right? This is like the infinity. Okay, and let us say both of them kind of make the same angle, phi a and phi a. Okay, so how many numbers of angles are there? So there would be n minus m number of angles, right? That would be the difference between the number of poles and the number of zeros. Okay, so the net angle made by all open loop poles and zeros to the test point would just be, well, this guy, right, n minus m with a negative sign because I am dealing with poles times phi a, right. So there are two things here, right. So this will be phi a and phi a, 2 times of that, right, and then we are only interested in n minus m guys. Okay. So what should these angles do? So all these guys, they should satisfy the angle criterion. So what is the contribution at infinity to this guy? Okay. So the total angle contribution at S0 must satisfy the angle criterion. Okay. What is the angle criterion? It says that the angle should be odd multiples of 180 degrees. What is the angle contribution? That is this guy, minus n minus m phi a is this guy, and this means I can just compute phi a as 2q plus 1 times 180 degrees over n minus m. Okay. So this angle is now computed just by this thing. Okay, and this is not surprising, right? So let's do that the same example again, right? I start with 0, I start with minus a. Okay, and let's say, well, I know that these two guys go to infinity from some point. Okay, so what is phi a there? Phi a is, say, 180 degrees over what was n minus m there? It was 2 with the plus minus. Okay, so what I have is plus 90 and minus 90. That is what exactly happens, right? So this pole, it starts here and goes to infinity at an angle plus 90, and here the other guy, this guy starts from here and goes here at an angle minus 90. Okay, so that is what this guy tells us, right, that the n minus m branches, 2 in this case, that proceed to infinity, do so along asymptotes with angles which are depending on the number n minus m, right. Okay, if there are more of these guys, the angle will change accordingly. If there is only one, say for example, if this is, say, I am just looking at, say, 1 over s plus 1, for example, right, is my g times h. So I can just draw the root locus. So this is going to infinity, so the angle would just be minus 180 or plus 180, both are the same, right, either this or this. It will just keep on going to this side. Okay. Now, so these asymptotes, well, they will somewhere they will have some starting point, right, from on the plane, on the complex plane. So the centroid, or the point of intersection of the asymptotes with the real axis, is computed in this way. I guess I get the sum of all the real parts of the poles minus sum of all the real parts of the zeros divided by number of poles minus number of zeros. This will again be n minus m, n minus m. Okay. So where does this come from? Okay, so what was the open loop transfer function? That is k times g times h, right. So what I had was a set of zeros in the numerator, set of poles with m being less than or equal to n. Now I just do some high school algebra, just to say that, well, this I can write it as decreasing powers of m, s power m minus 1 with the coefficients being the sum of all these guys until I reach the last point. S power 0 will just be, sorry, here it will be, okay, yeah, it will be the sum of all these guys till I reach here where it will just be the product of all these guys. Okay. Similarly, the denominator, I start with s power n, the n minus 1 will be the product of all these guys, the sum of all these guys, and the s power 0 guy will just be the product of all these guys. Okay. So I am just dividing one guy with the other. So how does the characteristic equation look like? Characteristic equation, I am interested again in the solution of the characteristic equation. 1 plus k times g times h equal to 0 is what I am aiming to solve, right. Okay, so 1 plus k looks like this. I just add a 1 here and go here, right. So I just divide, right. I just get this guy down here and then see how it looks like. So what will be now the how will the denominator now look like? So it will have start with powers of n minus m, it will have powers of n minus m minus 1 and so on. Okay. So what will be the coefficients of s minus n minus 1? That will just be the coefficients of these guys, the sum of the poles minus the sum of all the zeros, and then you just have this series. Okay. And now where is my, I am looking again. So my axis is here and my test point is at infinity here, S0, this is my infinity. Okay. So if the test point is very far, which means I am looking at very large values of x, I can just do my analysis just with these two terms, right, and then I can the contribution of the remaining terms would be very small. I am really looking at really large values of s. So my characteristic equation can equivalently be written as 1 plus k times g times h is just this guys, right. So I just have 1 plus k s to the power of n minus m with a coefficient of 1 and s power n minus m minus 1 with the coefficients that is decided by the nature of poles and the nature of zeros. Okay. Now, okay, let's do something else now, right. So let me start with a transfer function which has n minus m repeated roots at some point sigma a, and it has no zeros. Okay. How will that look like? Well, the k times g, I just say you can assume h equal to 1 or just add h, does not really matter. So, k times g would be something like this, k over s plus sigma a n minus m. Okay. Now, again the characteristic equation, I just add 1 and I get this one. Okay. So, this characteristic equation, how will this root locus look like? Well, this root locus has no zeros and n minus m poles. Okay. So, this root locus of this open loop system here with h equal to 1 will have n minus 1 branches, all of them go to infinity. They start at sigma a. So, that is what it tells us, right. So, what happens when, so this is my sigma a, okay, and then there are say n of these roots, all n will go to infinity. So, some here, some to this here, whichever way they want to go. Okay, that is decided again by the nature of these things, right. So, I am looking at as equation like 1 plus k over this guy n minus m, and all these n minus m branches, they go to infinity. Okay. Now, let me just expand this a little bit, right. So, this is like s power a, s plus a power n kind of thing. As we do the binomial expansion, and in the denominator I have again powers of s n minus m, and then now I am just summing this way, right. So, if I just substitute this this formula directly, summation of all the poles. How many poles are there? N minus m. Where are the poles? At sigma a. So, therefore, the second term would simply be sigma a n minus m, which is the summation of all the values of all the poles, n minus 1 and so on. Again, for large values of s, I just stop here and say, well, this is a good approximation at largest values. Okay. Therefore, the straight line roots, the straight line root locus branches of the transfer function in this equation are asymptotes of the transfer function with centroid this one, right. So, everybody starts here and then they go to infinity. We will see how they go. So, this is just a very vague picture. So, do not really think that I am drawing something very correct here, just to give some vague idea of what is happening, right. So, this straight line root locus branches of the transfer function, which has sigma a poles, sigma n minus m poles at sigma a, and then the negative side, they are asymptotes of the transfer function with centroid sigma a. All the asymptotes start at sigma a. Okay. So, what is the relation between this here, right. So, we started with this one, right. We wanted to find out what is the centroid point of the asymptotes, where do the asymptotes intersect, if at all, right. So, compare this guy, right, again. So, what did I assume here is I assumed here that, of course, I started with m poles, m zeros, n poles. I approximated my characteristic equation. I just did this, right. So, this was gone. Okay. So, this in a way the denominator of 5.3.11 and these are the same. Okay. If I just equate this, what I would get is something like this, n minus m sigma a is this guy. Okay. Now, what is sigma a in the general case? Because what I showed earlier when we were even looking at the angles is that if I start from here, this is my test point S naught, and these are two poles P1 and P2. If I look from very far, it might just seem as if these two poles are on the same location, because the angle contributions are almost the same. So, now I can take this analogy and I can just say, well, I can equivalently view this as a system where I have two poles minus sigma a. I am not changing the location of the poles, I am just seeing how they look like from infinity. So, how if there are two guys placed here at sigma a and sigma a in the left half plane, from infinity it will look, so these guys with P1 and P2 will exactly look like this, that are actually close to each other, and therefore, this centroid point of the asymptotes can be calculated this way, just by equating this expression here to this guy, because I know that from infinity it looks as if all the roots are together because they contribute the same kind of angle. Correct. Okay, so what is this guy? So the centroid point. So I sum the values of all the real parts of the poles, real parts of the zeros, and n minus 1, right? And this is how I calculate the centroid point. Okay, so let us see how it looks like, in terms of a small example. So take GS is k over s square plus 4. There are 3 poles for the system. Okay, again Hs is assumed to be 1. So wherever GS is given, you can safely assume that H of s is 1. Okay, and if we always know how to transform a non-unity feedback system to a unity feedback system, so we can do the same analysis. Okay, so coming back to this, so given a transfer function of this form, I have 3 poles and 3 branches of the root locus. Okay, so these 3 branches, let me just approximately draw something here, right? So I have a pole here. At origin s square plus 4 equal to 0, so I will have a complex conjugate pole at j2 omega and minus j2 omega or 2j omega, however you want to write this. Okay, so this, when k equal to 0, I am just here, right? K equal to 0 just at the poles, k equal to 0 at the poles, k equal to 0, my root locus looks like this, right? It satisfies the thing that I am symmetric about the real axis, and all of them go to infinity because there are no zeros. Okay. Now, how do they go to infinity? Now, first, the rule number 1 told me that it is symmetric. Rule number 2 told me that all will go to infinity. Rule number 3 told me about, well, is a point like this on the root locus? Is a point S0 which is on the real line on the root locus. Then I compute, well, see, if I am here, I just look at here and see how many poles are there. Well, there are 1, 2 and 3. There are no zeros. This is an odd number, and therefore this point will be on root locus, this point will also be on root locus. Any point on this real line, if I look towards my right, I will have 3 poles, which is an odd number. So this entire line will be on root locus, all the entire negative real axis. Okay. So what about the other 2 guys? So then we look at how do they go to, well, this guy goes to infinity in this way, right, because the entire real line is on the root axis. Now, how do the other guys go, right? So I look at the way they go to infinity, what kind of angles they make. Okay. So the angle here is computed as, again, 2 cube plus 1 over 3. So I get 60, 180 and 300. 60 is this guy, then I have 180 and I will have 300 here. 300 I can also write as minus 60. Okay, so this is okay here, right, because at 180 already this guy is branching out at 180 degrees. So this is a good validation. And then these guys, they will, so these are how my asymptotes go. So these guys will meet this line at 60 degrees at infinity, and this guy will meet this line at infinity, the guy at minus 2j omega. Okay. So at infinity, not that they just come here and then they go along, right. So they keep moving and they meet this line asymptotically. This guy meets this line asymptotically, right. Okay. So this is about the angles. Okay. So next, where do these asymptotes originate? And I just look at this formula here about computing the sum of the real parts of the poles, real parts of the zeros with n minus m. Okay. So this is 0 minus 0 and I have 3 and this 0. So these asymptotes actually start here and just go here, right? So they meet exactly at this point. Okay, so now how the root locus will look like? Well, this guy will start moving little towards this direction. We will see what direction exactly it moves in a little later. But I can fairly assume it moves something here. It never touches this line, right? It just goes here and then it only touches it at infinity. This guy starts moving this way, just a mirror image of this, and then goes to infinity this way. Okay, so we have found out which direction these guys go, or at least I know that now. Okay, this I may not exactly know this direction now, but I know that at infinity it meets this line, and therefore it has to move somewhere vaguely in this direction, right? And we will define this a little later. Similarly with this guy. Okay, so we know how, in what way or what decides how these roots branch out to infinity. Okay, so again coming back to the first example. So, I start at 0, I start at minus a, and I know here that this guy moves here, this guy moves here, they both meet at minus a over 2 and then go to infinity. Okay. And this point where they meet and then they again go away, right, they do not really stay together. You just come here, come together, just say hello and then go in your own path, right. So, now who decides where this is, why minus a by 2, why not something here, why not something here. Again this I know because I could just compute from the computations of my quadratic equation, but what in general, right, I may not be able to again compute all the roots and then it might be a little cumbersome. So, this was good enough for understanding. So, who decides this point and does that point exist, right, that also is the thing. So, if I am just giving you a characteristic equation which has a polynomial of order 9 plus 16 S8 and lots of things, I should first know that does a breakaway point exist or not, right. So, okay, who tells me that? Again everything is from the characteristic equation. Now, let us assume, so at this point what happens, that there are multiple roots, right, the root here, the root is 0, the root is minus a or the poles, and then they come here, here both the poles have the same value, minus a by 2 and minus a by 2. Okay. So, when this happens, my characteristic equation 1 plus k g times h, well, I will have here a root at S0 with some multiplicity r, okay, and times x of s. Again this x of s does not contain this factor, okay, and we will be interested in situations where r is at least 2, right. Okay. Now, I differentiate this guy, I differentiate this on the left hand side, I have d over ds of this guy, on the right hand side I differentiate again with respect to s. Differentiating with the first guy, I will have r minus 1 x s, then again the same guy here and x prime s, where x prime s is again the derivative of x of s with respect to s. Okay. Okay, let us leave this here for a while and then come back to this again. Okay. So, in the pole 0 form I can write 1 plus g 1 plus k times g times h as 1 plus k some polynomial in the numerator and some polynomial in the denominator. Okay. Now, let us see what this guy has to do. So, I can differentiate this guy and what I have is this thing. Here exactly I was just doing the same thing, right. I am differentiating this and I am differentiating this again here. So, in terms of p and q, the condition that dh or dh by ds equal to 0 looks like this, just the numerator being equal to 0. Okay. So, now look at this guy here. So, I know, okay, of course at S0, if this is S0 is a root, the characteristic equation is obviously 0. Now, look at the derivative, right. The derivative, what is the value of derivative at s equal to s naught? Well, at s equal to s naught, well, this guy goes to 0, this guy also goes to 0. So, d over ds, this, so in this expression d over ds of k gs sh at s equal to 0 is 0, so s equal to s naught, where s naught comes with the multiplicity of r. Okay. So, that is what this means. Right? So, the roots of this equation are the roots of this guy. Okay. Now, I can equivalently write my characteristic equation something like this. So, 1 plus k g times h or 1 plus k p over q, I can just write it as k equal to q over p. Okay. Okay, that is the reason why we are doing this now. So, first is, well, I am just looking at how to detect if there are multiple roots, and that is when d over ds of 1 plus k times g times h goes to 0, that has a multiple root, right, at that point, right, and that point here is so therefore, I can just say that, well, the solutions are of this form, right. Now, let me do this another something else. So, k is again now a function of s, dk by ds, looks like this. And when does dk by ds go to 0? Dk by ds goes to 0 when the numerator of this guy goes to 0, that is p q prime minus q p prime. Now look at these two, these two are the same. Sorry, this expression and this expression are the same, right. Now the equivalent, the condition here, so when does R have a multiplicity at least 2? Sorry, if R was just 1, dk by ds would not be 0, it could be something else, because this guy would go away. But if R is 2, this guy would go to 0, this guy would also go to 0. So if S naught occurs twice, it means d over ds of k times g times h equal to 0, right. So if S naught occurs twice, that meant that d over ds of 1 plus k g h is also equal to d over ds of g times h equal to 0, and we can have the k or not. Okay. Now this being 0 tells me that there is a multiple root. This being 0 also means that this is 0. Okay. Now compare this condition and compare this condition here. Okay. They both are the same, and therefore I can check I can just equivalently say dk by ds equal to 0, this is equivalent to d by ds of 1 plus k g h being equal to 0. And for obvious reason, this is for me easy to compute, because I know q and p. And this might be because I may have to, g and h might have numerators, denominators, I may have to do a lot of other stuff, but then this is easier to compute. So this condition tells me that there is a breakaway point, right. The breakaway points are the points at which multiple roots of the characteristic equation occur, and the solution of this will be the exact breakaway point. You can compute this. I think here it would be very trivially satisfied. Okay. So let us again compute for this example and check, right, in this way of why this is minus a by 2. So what was the characteristic equation? That was 1 plus k over s plus a is 0, or k was minus s plus a. Okay. dk by ds would be minus twice s plus a, and if I equate this to 0, I get the solution as s equal to minus a by 2, right, and this is the breakaway point. And of course, in this case it also turns out to be the centroid point, and it can happen in many cases, right. So this is like, okay, you can see why this is a by 2 using this explanation over here. Okay. So let's do a sketch a root locus for this guy. So I have again a pole at minus 2, minus 3, minus 4, 0 at minus 1, 3 poles, 1, 0. Again, the number of branches in the root locus would be the number of poles, that is 3, and these 3 branches, one will go to the 0 at minus 1 and the other 2 will disappear to infinity, right. Again, starting from k equal to 0, they will start at the poles and then go to infinity, right. Okay. So let us first draw the basic conditions. Okay. So at k equal to 0, my root locus will be at these poles, this is minus 2, minus 3 and minus 4. Okay. So rule number 3, which part of the root locus on the real line or the real axis will be on the root locus? Okay, let us start from here. Well, there is nothing here, so there won't be anything here. So and then let us look at this area between minus 1 and 2. If I look to the right, there is 1, 0. So I am good here, right? There is an odd number, this one. Okay. Now look at the area here between minus 2 and minus 3. how many guys are sitting out here? 1 pole, 1 0, that is an even number, I do not like it. So, I just go here between minus 3 and minus 4, okay, I just look to the right. So, there is 1, 2 and 3, oh it is an odd number, so I like it, right, it is here. And then what happens after minus 4, I just look to the right, I have 1, 2, 3, 4, okay, so this area is also not good for me. So, one thing for sure I know that okay, k equal to 0 points are these guys, k equal to 0, k equal to 0, k equal to 0, this guy will go quickly and then sit here, right. Now, these guys have to find their way to infinity, they both try to run away this way, right, but it is not allowed because these points are not on the root locus. So, they have to somewhere just be around this one and then decide how to go to infinity. Okay. Now, let us see who tells these guys where to go to infinity. Right. Okay. So, how do they go to infinity? There are two guys who are going to infinity and they proceed to infinity along asymptotes with angles again given by 2q plus 1 divided by n minus m, at n minus m was 2. So, you will have 90 and 270. Okay. So, I know at least that so these two guys, again let me just draw it for convenience. So, I have a 0 here, this is at minus 1, minus 2, sorry, these are all poles, pole, a pole, the pole. So, whatever they do in between, they will go to infinity at these angles, 90 and 270. Okay. So, how is the centroid point given? The centroid point where of this is again you compute the sum of the poles, all the real parts and zeros, and you get this one. Okay. Now, what I also know is that okay, now this is a centroid point, right. So, the asymptotes will be like this at minus 4. So, these guys will move and then they will meet these guys at infinity, and where do these lines at infinity come from? They come from minus 4. So, I know that one now, right. So, I will just remove this. So, I did not know which direction they go to infinity, but now I know that they go from minus 4. Now, the next thing is okay, these guys, well, where do they meet? Does this guy wait for this guy to come all the way here and then they just move away, or they meet somewhere in the middle, or and then go to and then move apart? Okay. So, that is we will find. So, there is a breakaway point, right. Is breakaway point minus 4 or minus 3 or whatever, let us just try to find that, and that is given by solution of dk by ds equal to 0. Okay. So, I just do all the math here, dk by ds equal to 0 would mean, well, it gives me 3 roots, minus 3.5, minus 2 and 0.126. Okay. Now, look at these points, minus 2, that these regions are not on the root locus, this region is not on the root locus, this region is not on the root locus, this region is not on the root locus. So, only point where they are allowed to meet is minus 3.5. Okay. So, that is the point here. So, what happens is, well, this guy goes here, these two guys from the asymptotes in the centroid computation, I know that they will meet these two lines at infinity. So, they will just start from here. So, this guy starts here and goes to infinity, this guy starts here and goes to infinity along this line, right. So, that is the way we compute. So, we will again how do they move, why not they do something like this, or something like this, more. So, that we will see a little later, but at the moment just interested now little towards the asymptotic behavior of this. Okay. So, we'll end this lecture over here, and then we will see a little more details and then conclude the root locus by looking at the last 3 rules. Thank you.